The topic tonight is refrigerant control devices. A refrigerant control device handles the amount of liquid passing between the high and low side of the system. There are several different types that we will be covering. You will be expected to draw a working diagram of each control, plus list the important operating parameters. Automatic expansion valves are designed for constant loads. A critical charge, between plus and minus 3%, is necessary for proper performance. The bleeder diameter is 1/2 the diameter of a human hair. An inlet screen is the last defense against crud, with 60 to 100 grids per inch. The diaphragm has concentric rings. The spring is steel, with the body being bronze or brass. The needle is stellite, and the seat is Monel. A better design uses bellows, but also more expensive. Notice that the adjustment spring is on the top of this device. Remember, this valve is only suited for constant loads. Its performance suffers when outside its design range. An automatic expansion valve utilizes 3 pressures: low side, air, and spring. Air pressure and spring pressure work together to balance low side pressure. The technician must adjust the spring pressure for higher altitudes. This diagram is a student drawing from a past class. You may draw this version, or this one, it is your choice. Whichever one you choose must have all the parts labeled, plus verbiage that shows you know the material. The thermostatic expansion valve is a metering device which controls the flow of liquid refrigerant entering the evaporator, by maintaining a constant superheat. This fact alone requires that subcooling be used to charge a system. Do not charge using superheat. The valve provides the most widely used refrigerant control for both commercial and industrial facilities because of its high efficiency and adaptability to any type of refrigeration application. It is the only valve that ensures that the liquid cannot return to the compressor. When too much liquid enters the evaporator, it may not all boil off, which could result in liquid entering the compressor. The bulb helps prevent this happening by sensing the low temperatures at the evaporator outlet and then controlling how much liquid enters it. The standard thermostatic expansion valve has 3 main functions. 1. Provide a constant amount of superheat under varying load conditions, provided that the load is within the design range. 2. Keep the entire evaporator full of liquid and vapor refrigerant under all loads. 3. Prevent liquid flood back of refrigerant to the compressor under all design loads. The 3 main working forces acting on the thermostatic expansion valve are sensing bulb, spring pressure, and evaporator pressure. The sensing bulb provides a closing force, while both spring pressure and evaporator pressure provide an opening force. Many people consider the TXV to be capable of solving all refrigerant problems. A standard TXV cannot, I repeat, cannot control evaporator pressure, cannot cycle the compressor, cannot control running time, or cannot control box temperature. Remember, its function is to provide a constant superheat. This diagram has a power ball piston, one of several types of TXVs. The sensing bulb is connected to the body of the thermostatic expansion valve by a capillary tube between 10 and 15 thousandths of an inch thick. It is usually gas-filled, but liquid is not uncommon. Exotic bulbs may be cross-charged. This means that a different refrigerant is used in the bulb than in the rest of the system. Now let's discuss installation of the sensing bulb. Clean the suction line near the outlet of the evaporator. The entire length of the sensing bulb must be in contact with the clean portion of the suction line. The sensing bulb should be placed several inches downstream of the external equalizer connection. The sensing bulb should be attached at 12 o'clock on any suction line of 7/8 inch diameter or smaller. On lines larger than 7/8 inch diameter, the bulb should be placed at either 4 o'clock or 8 o'clock. The bulb should never be placed at 6 o'clock due to liquid in the capillary tube. Always insulate the sensing bulb after installation. The thermostatic expansion valve can be adjusted by altering the tension of the spring in the valve, sometimes referred to as the superheat adjustment. A lot of superheat is usually not required as the effective heat transfer area of the evaporator is reduced. However, if the superheat is set too low, the valve will lose control of the refrigerant flow and the evaporator will alternatively starve and overfeed, creating a condition called hunting. Under normal conditions, do not adjust, I repeat, do not adjust. Overall, the thermostatic expansion valve is a sophisticated control device. It is considered the most energy efficient of all valves commonly found in the residential and light commercial environment. Hi, this is Ryan. I'm going to have Heather do the next topic. Please let the instructor know what you think of her.
The low-side float expansion valve controls the liquid refrigerant flow where a flooded evaporator is used. It consists of a ball float in either a chamber or the evaporator on the low-pressure side of the system. The float actuates a needle valve through a lever mechanism. As the float lowers, refrigerant enters through the open valve. When it rises, the valve closes. In a high-side float expansion valve, the valve float is neither a liquid receiver or an auxiliary container on the high-pressure side of the system. Refrigerant from the condenser flows into the valve and immediately opens it, allowing refrigerant to expand and pass into the evaporator. Refrigerant charge is critical. An overcharge of the system floods back and damages the compressor. An undercharge results in a capacity drop.
The capillary tube is a fixed refrigerant control which acts as a restriction device and should not be altered. Care must be taken to replace, like with like. A fixed orifice means that there is no means of adjusting for load changes. The two factors involved with capacity are length and bore, where bore is the inside diameter. If the cap tube is too long or the bore is too small, the evaporator will starve. If the cap tube is too short or the bore too large, the evaporator will flood. The cap tube is easily plugged, so must have a filter dryer installed to catch crud. It is used in both residential and commercial systems, and common in domestic refrigeration. Constructed of thin copper tubing, its length and internal dimension cause liquid to back up, creating a high-pressure side, and dropping to a low pressure at the outlet. For comparison, think of a drinking straw. If you pinch the straw while blowing into it, the straw contains high and low sides. This diagram shows a typical cap tube system with a diagonal line separating the high and low sides. Cap tubes are sized to provide optimum performance at a single operating condition. They do not operate well on systems having a range of loads.